Welcome back to another video in my wild networking series. I'm going to be finishing up the topic of ARP scaling, and then the next topic will be BGP. So last video I left off with this part of RFC 6820, which is about ARP scaling and problems when it scales. In addition to reading these RFCs, we're also going to keep in mind some real-world questions, such as why is my internet so slow, that you'll hear. So we're going to be always focusing on that sort of question and keeping track of potential answers and things that we can check or discuss when this question comes up. But the goal of this video is just to finish reading this RFC, and then in the next video we'll be moving on to learn about BGP. Address resolution in IPv4. In IPv4 over Ethernet, ARP provides the function of address resolution. To determine the link layer address of a given IP address, a node broadcasts an ARP request. The request is delivered to all portions of the L2 network, and the node with the requested IP address responds with an ARP reply. ARP is an old protocol and by current standards is sparsely documented. For example, there are no clear requirements for retransmitting ARP requests in the absence of replies. Consequently, implementations vary in the details of what they actually implement. Oh, this one doesn't even have a link. Okay, so here's the original internet standard for ARP. Oh, but it's been, oh, these are updates to it. From a scaling perspective, there are a number of problems with ARP. First, it uses broadcast, and any network with a large number of attached hosts will see a correspondingly large amount of broadcast traffic. The second problem is that it is not feasible to change host implementations of ARP. Current implementations are too widely entrenched, and any changes to host implementations of ARP would take years to become sufficiently deployed to matter. That said, it may be possible to change ARP implementations in hypervisors, L2/L3 boundary routers, or in top of rack access switches, to leverage such techniques as proxy ARP. Finally, ARP implementations need to take steps to flush out stale or otherwise invalid entries. Unfortunately, existing standards do not provide clear implementation guidelines for how to do this. Consequently, implementations vary significantly, and some implementations are chatty in that they just periodically flush caches every few minutes and send new ARP queries. Address resolution in IPv6. Broadly speaking, from the perspective of address resolution, IPv6's neighbor discovery ND behaves much like ARP, with a few notable differences. First, ARP uses broadcast, whereas ND uses multicast. When querying for a target IP address, ND maps the target address into an IPv6 solicited node multicast address. Using multicast rather than broadcast has the benefit that the multicast frames do not necessarily need to be sent to all parts of the network. For example, the frames can be sent only to segments where listeners for the solicited node multicast address reside. In the case where multicast frames are delivered to all parts of the network, sending to a multicast address still has the advantage that most, if not all, nodes will filter out the unwanted multicast query via filters installed in the network interface card, NIC, rather than burdening host software with the need to process such packets. Thus, whereas all nodes must process every ARP query, ND queries are processed only by the nodes to which they are intended. In cases where multicast filtering can't effectively be implemented on the NIC, for example, as on hypervisors supporting virtualization, filtering would need to be done in software, for example, the hypervisor's virtual switch. This is really good. Like, I really feel like this video and the last video are like the perfect uses of my time to, sometimes, but reading RFCs is really underrated. That's something I really haven't done a lot in my professional, in my education and training. I'm more focused on like certifications and courses, and I went to networking school, and official documentation from like a vendor I've focused on, but like the RFCs themselves I really haven't focused too much on, and I'm really happy with this one. Number 6, generalized data center design. There are many different ways in which data center networks might be designed. The designs are usually engineered to suit the particular workloads that are being deployed in the data center. For example, a large web server farm might be engineered in a very different way than a general purpose multi-tenant cloud hosting service. However, in most cases, the designs can be abstracted into a typical 3-layer model consisting of an access layer, an aggregation layer, and the core. The access layer generally refers to the switches that are closest to the physical or virtual servers. The aggregation layer serves to connect multiple access layer devices. The core switches connect the aggregation switches to the larger network core. Figure 1 shows a generalized data center design which captures the essential elements of various alternatives. So are these top of rack switches? I don't know what the TN stands for. Because, yeah, so we can see core stands for core, AGGR stands for aggregation, but T, I don't understand what T stands for. But it looks like this is what they mean by top of rack switches. They mean like the access layer switches. That I wasn't clear about, but I think that is the case. But what is an end of rack switch then? I'm curious about that. Access layer. The access switches provide connectivity directly to / from physical and virtual servers. The access layer may be implemented by wiring the servers within a rack to a top of rack switch, or less commonly, the servers could be wired directly to an end of rack switch. A server rack may have a single uplink to one access switch, or may have multiple uplinks to 2 different access switches. Okay, cool. I never really, my experience first of all, my experience has been largely in service provider, but this, as I said before, this RFC is like perfect. I'm really glad I'm reading this right now. The aggregation layer. In a typical data center, aggregation switches connect many TOR, top of rack switches, or access switches. Typically, there are multiple. Yeah, so you have the rack, as we see here, with your access layer, top of rack switches. and then all your servers are going to plug into those switches, and they're going to be in the rack there. In a typical data center, aggregation switches connect many top-of-rack switches. Usually there are multiple parallel aggregation switches serving the same group of top-of-rack switches to achieve load balancing. It is no longer uncommon to see aggregation switches interconnecting hundreds of top-of-rack switches in large data centers. Core switches provide connectivity between aggregation switches and the main data center network. Core switches interconnect different sets of racks and provide connectivity to data center gateways leading to external networks. Next part is L3/L2 topological variations. L3 to access switches, something we learned about before. In this scenario, the L3 domain is extended all the way from the core network to the access switches. Each rack enclosure consists of a single L2 domain, which is confined to the rack. In general, there are no significant ARP/ND scaling issues in this scenario, as the L2 domain cannot grow very large. Such a topology has benefits in scenarios where servers attached to a particular access switch generally run VMs that are confined to using a single subnet. These VMs and the applications they host aren't moved or migrated to other racks that might be attached to different access switches and different IP subnets. A small server farm or very static compute cluster might be well served via this design. Okay, so this is a design that doesn't have any aggregation switches. It just has core switches with L3 down to the edge switches. Yeah. L3 to aggregation switches. When the L3 domain extends only to aggregation switches, hosts in any of the IP subnets configured on the aggregation switches can be reachable via L2 through any access switches if access switches enable all the VLANs. Such a topology allows a greater level of flexibility, as servers attached to any access switch can run any VMs that have been provisioned with IP addresses configured on the aggregation switches. In such an environment, VMs can migrate between racks without IP address changes. The drawback of this design, however, is that multiple VLANs have to be enabled on all access switches and all access-facing ports on aggregation switches. Even though L2 traffic is still partitioned by VLANs, the fact that all VLANs are enabled on all ports can lead to broadcast traffic on all VLANs that traverse all links and ports, which has the same effect as one big L2 domain on the access-facing side of the aggregation switch. In addition, the internal traffic itself might have to cross different L2 boundaries, resulting in significant ARP/ND load at the aggregation switches. This design provides a good trade-off between flexibility and L2 domain size. A moderate-sized data center might utilize this approach to provide high availability services at a single location. L3 in the core only. In some cases where a wider range of VM mobility is desired, for example, a greater number of racks among which VMs can move without IP address changes, The L3 routed domain might be terminated at the core routers themselves. In this case, VLANs can span multiple groups of aggregation switches, which allows hosts to be moved among a greater number of server racks without IP address changes. This scenario results in the largest ARP/ND performance impact, as explained later. A data center with very rapid workload shifting may consider this kind of design. Yeah, because you get, so the disadvantage of having L3 at the core, extend down to the access layer, is you've got to do more IP address changes. So if you're constantly swapping things in and out, especially if you're using VMs and you're doing it like with, hundreds of devices per hour per minute, it's going to make more sense to abandon those abandon layer 3 at the edge and just have it in the core only, so that you don't have to manage as many IP address changes. Alright, next part is overlays. There are several approaches where overlay networks can be used to build very large L2 networks to enable VM mobility. Overlay networks using various L2 or L3 mechanisms allow interior switches/routers to mask host addresses. In addition, L3 overlays can help the data center designer control the size of the L2 domain and also enhance the availability of multi-tenancy in data center networks. However, the use of overlays does not eliminate traffic associated with address resolution. It simply moves it to regular data traffic. That is, address resolution is implemented in the overlay and is not directly visible to the switches of the data center network. A potential problem that arises in a large data center is that when a large number of hosts communicate with their peers in different subnets, all these hosts send and receive data packets to their respective L2/L3 boundary nodes, as the traffic flows are generally bidirectional. This has the potential to further highlight any scaling problems. These L2/L3 boundary nodes have to process ARP/ND addresses in the target subnets for what are generally bidirectional flows. Therefore, for maximum flexibility in managing the data center workload, it is often desirable to use overlays in place of related groups of hosts in the same topological subnet to avoid the L2/L3 boundary translation. The use of overlays in the data center network can be a useful design mechanism to help manage a potential bottleneck at the L2/L3 boundary by redefining where that boundary exists. I kind of want to get out the lab at this point because I just want to have things kind of more driven home for me, and I think a lab would do that. So let's do design. So I'm gonna make a new project in GNS. It's going to be called Designs, and then oops, I'm not going to get the new version of GNS. That would be a nightmare. It'd be great if I could move GNS to another. Let's see here. So edits, preferences. Okay, well, I don't see how I can make this less awful. It's stuck on my second monitor. I'm trying to get this GNS to show up on the other. Oh, perfect. Okay, it was stuck in full screen mode. I figured it out. Okay, so yeah, let's get some routers down and focus on some designs. So we can have layer 3 at the edge. We can have layer 2 at the edge, but we can use these MXs, and they have VLAN bridging on them, so we can use VLANs and we can do everything. So let's pretend that we've got a rack. Yeah, so we'll make it look like this. There we go, and here's our oops, and we'll send it to back. Perfect. Okay, so here's our top of rack switch. So then we're gonna have some servers inside the rack. So we'll have a few of these. Let's have an Ubuntu. Let's have this network automation server. Oops, and it looks like that got sent to back. Or actually, I'm not sure what happened to that. But, oh, here it is. Okay. Okay, so we've got some servers in here. We've got the network automation server. Let's get an Ubuntu Docker guest server. And then let's just get a regular VPCS server as well. Okay, so this is our access layer. Let's have 3 of these. Okay, I can't just copy and paste it. But I probably can. No, I can't. Okay, well, shoot. How do I do this? Okay, so let's have, we're gonna have 3 racks in our data center here. Then we're also gonna have another rack for the distribution layer. But in the meantime, let's get more Ubuntu Docker guests lined up here. Yeah, I might as well just make everything an Ubuntu Docker guest. I'm starting to get really tired too. And I'm only 24 minutes in. I need to go longer than that. I guess I can cut it off at a half an hour, hour and a half day studying isn't is gonna be, I think, fine. Okay, so here's my on there. We've also got the distribution layer and the core layer. So here's the distribution layer. Let's have two of these devices at the distribution layer. Okay, and then we have a device at the access layer as well. Or sorry, at the core layer. There we go. Okay, so I'm going to cable these up. Oops, that's not the cable. How do I get rid of that now? Usually I have like a pointer. Oh, here it is. Okay. Oh, and I'm really starting to get tired and not expecting to get this tired this soon. But that is definitely happening. Okay, so now we're definitely gonna have links, two links here, and then links there. But the easy ones we're gonna have links like this. Okay, so we've got that going on. Now here's where the point of contention is. We've got to think about what we want, but I'm pretty sure we're going to have a link to each of these, and then a link to each of this, and then we'll probably even have a link here as well. So let's do that. So here we're going to have 0, 2, 0, 1, 2, 1, and then 2. Oh, okay. Yeah, I think I haven't made any mistakes yet. Oh, and I'm really tired. I was not expecting to be this tired this soon. I'm kind of upset that I'm this tired this soon, to be honest. Okay, so here's the network I'm going to be playing around with. Let me boot it up. Okay, and we'll keep reading the RFC. These are factors that affect data center design. Oh, and I really am tired. Like, I'm really running out of steam. Let's stop it here, actually. I'm just too tired. So yeah, unfortunately I'm gonna stop it here. It's just a half an hour video. I would have liked to go an hour, but I'm just absolutely tired, so What the heck? Jungles and animals? I don't understand. Okay, but we will come back to this tomorrow. I'll try to do at least one video tomorrow, if not two. Oops, looks like my camera stopped, so I'll reactivate that. Okay, and that'll be the end of this video. Unfortunately, I could only do an hour, but thanks for watching, and I'll see you in the next one.